Hello everyone and welcome to my channel, Short Pros in Classical Mechanics. I would like to bring you today an exercise, well, not really an exercise, it is a theoretical demonstration of the position vector, velocity and acceleration in different coordinate systems. When I was doing my degree, this was pivotal in my study of classical mechanics, a very important exercise to later tackle problems. And it is just, as I said, expressing position, velocity, and acceleration in Cartesian, cylindrical, and spherical coordinates. Cartesian coordinates, we've got a point there, and we know that we can describe or locate the point with x, y, and z, the Cartesian coordinates. In cylindrical coordinates, the same point, we got there the height, z coordinate, and instead of x and y, we have the distance from the origin to the projection of the point on the x and y plane. We call it r, and the angle that this distance that r makes with one of the axes, let's say the x-axis, and we call it phi. And in spherical coordinates, we got the point there, and we got the distance directly from the origin to the point. This is r, one of the coordinates. Then the angle that this r makes with the z-axis, with the vertical axis, the projection on the xy plane, and the angle that this projection of r makes with the, let's say, x-axis, that is phi, angle of the projection of r on the xy plane with the x-axis. So let's get started. We've got a single particle along a trajectory, and we are going to describe it in the Cartesian system. We've got z, y, x, and we've got the unitary vectors in the direction where x increases, ux, where y increases, uy, and where z increases, uz. So the position vector is simply x ux, y uy, plus z uz. To get the velocity, we just have to derive the position vector in time. And in principle, although probably most of you are familiarized with this, applying the chain rule, Leibniz rule of derivatives, we've got the derivative of the first and the derivative of the second, keeping the first constant. So we derivate the coordinates, and we would, to be in pure, derivate the vectors, the unitary vectors. But the unitary vectors are always constant during the motion along the motion of the particle. So coordinates vary, vectors do not. So this bracket here is just 0, and that is the expression for the velocity x dot ux plus y dot uy plus z dot uz, where dot means simply derivative in time. The acceleration vector is simply the derivative in time of the velocity, and it is just the second derivative of the coordinates with the corresponding unitary vectors. This is, I think, probably most of you are familiarized with this. In cylindrical, we've got that x, the coordinate x, is just by trigonometry r cosine of phi. The y coordinate is r sine of phi, and the z coordinate is z. There we've got the usual basis, ux, uy, uz, and we are going to introduce a new orthonormal basis formed by these three vectors here. Ur in the direction where r increases, this one here. U phi in the direction where phi increases and perpendicular to ur, and uz in the direction where z increases, and it is the same vector than the Cartesian uz, because z is the same coordinate, doesn't change from Cartesian coordinates to cylindrical coordinates. So that angle here is the same as this is phi, and we can decompose the new vectors in terms of the Cartesian vectors. UR is cosine of phi ux plus sine of phi uy. If this angle here is phi, this is 90 minus phi, and this is phi again. So u phi, that angle is phi there, u phi is minus this distance here, but pointing in the negative direction of x. It would be minus sine of phi ux plus cosine of phi, this little distance here, uy. And uz is the uz of the Cartesian, the same. So the position vector is, we start from the Cartesian expression, and we just simply substitute the coordinates. So x is r cosine of phi us plus r sine of phi uy plus z uz. We take out r from the brackets, and it's r multiplying cosine of phi us plus sine of phi uy and plus z uz. But this here, inside of the bracket, is u sub r. So finally, the position vector in cylindrical coordinates is r u sub r plus z u sub z. To get the velocity vector, we just simply have to derivate in time the position vector, and applying the chain rule, this would be r dot ur plus z dot uz plus, and now we have to derivate the unitary vectors, keeping the coordinates constant, plus r ur dot plus z uz dot. When the particle moves along its trajectory, coordinates are varying, and so do the unitary vectors ur and u phi. Ur has changed from this vector to this vector, and u sub phi has changed from this vector to this vector. So they are not constant in time, because they depend on the angle. They depend on the angle here, which varies in time. So ur dot, derivating with respect phi, is minus phi dot sine of phi ux plus phi dot cosine of phi uy. If we take common factor phi dot, this is phi dot multiplying minus sine of phi us plus cosine of phi uy, and this is simply phi dot u sub phi. Following a complete analog procedure, if we derivate in time u phi, this is minus phi dot cosine of phi us minus phi dot sine of phi uy. And again, if we take out common factor, minus phi dot multiplying cosine of phi ux plus sine of phi uy. But this inside the bracket is ur. So the derivative in time of u phi is minus phi dot, the derivative of the coordinate in the direction ur. So we just substitute ur dot here, and of course the derivative in time of uz is 0 because it remains constant. So we substitute ur dot here, and we would get, this remains the same, r dot ur plus z dot uz and r multiplying phi dot u sub phi. And this is the expression for the velocity in cylindrical polar coordinates. To get the acceleration, we simply need to take the derivative in time of the velocity, and again we start derivating in time the coordinates, keeping the unitary vectors fixed, plus keeping what we have, the derivative of the coordinates, these expressions here, and derivating in time the unitary vectors, just simply applying the chain rule. We just substitute what we calculated before. UR dot is phi dot U phi, and U sub phi dot is simply minus phi dot UR. Grouping everything together in terms of UR, U phi, and UZ, we get this expression here for the acceleration in polar coordinates. In spherical coordinates, we will have the radial coordinate r, that is the distance between the origin and the particle, the angle that this r makes with the z-axis, we call it theta. This distance here from the particle to the axis is r sine of theta. This is the right angle here, 90 degrees. And if we take the projection of the position of the particle with the xy plane, the vertical projection, this angle that r sine of theta on the xy plane makes with the x-axis is phi, and we can just relate the spherical coordinates with the Cartesian coordinates like this. X is simply, if this is r sine of theta, x is r sine of theta cosine of phi. Y would be r sine of theta sine of phi, and z would be r cosine of theta by simple trigonometry. Unitary vectors there, Cartesian unitary vectors, and we introduce an orthonormal basis of unitary vectors in spherical unitary vectors. U r in the direction where r increases, U theta in the direction where theta increases, perpendicular to UR, and perpendicular to both U phi in the direction where phi increases. Just to view it better, because maybe it's a bit small, we zoom this area here of unitary vectors. Here we've got the unitary vector UR in the direction where the radial distance from O increases, U theta in the direction where theta increases, and U phi in the direction where phi increases. If this is 1, the modulus of UR, this is simply, this distance here is sine of theta, same as this. And we can decompose UR in terms of the Cartesian vectors. UR would be sine of theta, which is this, cosine of phi ux, plus sine of theta, sine of phi uy, plus cosine of theta uz. This u sub theta, we bring it here. This is the same vector as this, and we are going to project it on the xy plane. We see here that this angle here would be the same as this, and we just simply project. This is cosine of theta, this distance here, the projection of u theta with the xy plane. This is cosine of theta, and we can bring it into the coordinate system. It will be u theta cosine of theta, cosine of phi ux, cosine of theta, sine of phi uy, minus sine of theta uz, because it's pointing in the negative z direction. And now u phi, we bring it to the xy plane. If this is phi, it's the same angle than this, phi there. And if we project, it is just simply minus sine of phi ux plus cosine of phi uy. So now we have all the ingredients to write the position vector, velocity and acceleration in terms of the spherical coordinates. The position vector, starting from the Cartesian coordinates and Cartesian unitary vectors, is x, ux, y, uy, z, uz. We simply substitute the coordinates. So r vector is r sine of theta cosine of phi ux plus r sine of theta sine of phi uy plus r cosine of theta uz. We take out r, and this is r multiplying to sine of theta cosine of phi ux, sine of theta sine of phi uy plus cosine of theta uz. But this here inside the brackets is simply ur. So in spherical coordinates, the position vector of a particle is the radial coordinate multiplied by the unitary vector pointing in the increasing r. The velocity, we just have to simply derivate. So we derivate r ur, and applying the chain rule is r dot u sub r plus r u sub r dot. When the particle moves along the trajectory, the coordinates vary, but so do the unitary vectors ur, u phi, and u theta. So the velocity is simply r dot ur, and now we derivate in time u sub r. If we derivate against theta, we've got derivating ur against theta is theta dot cosine of theta cosine of phi ux plus cosine of theta sine of phi uy minus sine of theta uz. The chain rule, first we derivate with theta and then multiply by theta dot. But also phi depends on time, so it will be plus r phi dot, we derivate against phi, and ur derivative against phi is minus sine of theta sine of phi ux plus sine of theta cosine of phi uy multiplied by phi dot, just applying the chain rule. But this inside the bracket here, cosine of theta cosine of phi ux cosine of theta sine of phi uy minus sine of theta uz is simply u sub theta. So this is y appears here, r theta dot u sub theta. And this second bracket here, what it is inside is u phi. So finally, the velocity is that thing there, r dot ur plus r theta dot u sub theta plus r phi dot sine of theta u phi. We just took out here sine of theta that multiplies minus sine of phi ux plus cosine of phi uy, and this is u phi. This is just simply taking care and being patient, doing derivatives, and just substituting. The acceleration vector is just the derivative in time of the velocity. So we get the velocity there, and again, we start derivating the coordinates, and then we derivate the unitary vectors. The unitary vectors, we got them before decomposing, and as the particle moves along its trajectory, we know that the unitary vectors vary in time. So again, as we did before, maybe it's better to write it in detail. U sub r dot is both theta and phi depend on time, so I have to derivate with both. So I start with theta. This is the derivative in time of ur would be theta dot cosine of theta cosine of phi ux plus cosine of theta sine of phi uy minus sine of theta uz. And now plus the derivative with phi, that would be minus sine of theta sine of phi ux plus sine of theta cosine of phi uy multiplied by phi dot. Just simply the chain rule. And now we substitute what is in brackets. This thing here is u sub theta, and this thing here is, if we take out sine of theta from both from both terms. This would be sine of theta phi dot that multiplies minus sine of phi ux plus cosine of phi uy, and this is simply u phi. Doing a complete analog procedure, we derivate u sub theta. First, we start with the dependency in time of theta, so it is theta dot multiplying minus sine of theta, derivating in theta minus sine of theta cosine of phi ux minus sine of theta sine of phi uy minus sine minus cosine of theta uz, derivating with theta. And now we derivate with phi multiplied by phi dot. So phi dot multiplying minus cosine of theta sine of phi ux minus cosine of plus cosine of theta cosine of phi uy. And this thing here doesn't depend on phi. So this thing inside the bracket is ur. If we take out the minus sign, sine of theta cosine of phi ux plus sine of theta sine of phi uy plus cosine of theta uz is simply ur. So this is why it appears here as minus theta dot ur. Plus, if we take out cosine of theta, this is phi dot multiplying cosine of theta minus sine of phi ux plus cosine of phi uy. And this is simply u sub phi. And finally, if we derivate in time u phi, it just depends on phi. So phi dot that multiplies cosine phi ux plus sine of phi uy with the minus sign. We take it out. So this is simply minus phi dot, and this is not directly a vector, but this is not directly a vector of the basis, but we see here that if we multiply sine of theta by ur, this will be sine square of theta cosine of phi ux plus sine square of theta sine of phi uy plus sine of theta cosine of theta uz. And if we multiply cosine of theta multiplied by u sub theta, this would be cosine of theta cosine square of theta cosine of phi ux cosine square of theta sine of phi uy minus sine of minus cosine of theta cosine of minus cosine of theta sine of theta uz. And the sum is just simply this. This would be simply cosine of phi ux plus sine of phi uy. Just being careful. If needed, you just develop this product here, and you see that it is exactly this, cosine of phi ux plus sine of phi uy. So finally, all we have to do is just substitute in terms of the spherical unitary vectors the derivatives of the unitary vectors. If we do so, we just get, we substitute. So u sub r dot is theta dot u sub theta plus sine of theta phi dot u sub phi. U sub theta dot is minus theta dot ur plus cosine of theta phi dot u phi, and u sub phi dot is minus phi dot sine of theta ur plus cosine of theta u theta. So grouping in terms of the unitary vectors without dot, we get this expression here, this long expression there. And this is the expression for the acceleration of the particle in spherical coordinates. So the best thing with this is to put it in on a sheet of paper to tackle. Then we have these tools to tackle problems in mechanics, and write it, get it in a sheet of paper, and when needed, you just go to this sheet of paper, and whatever you need. If, for example, you have a problem in a cylinder, you will use the cylindrical coordinates. A problem in a sphere, you use spherical coordinates. And I would like to bring you some examples of this. So, for example, we have a shoebox size A, B, and C, and imagine we have a particle that moves along the y-axis, one of the sides. So the description of this is x is constant, z is constant, the height, and the only thing that varies is y. So the position vector is simply x0, let's say that x is x0, that it is constant, and z is z0, that it is constant. So the position vector is that. The velocity is just simply, as we've seen, the velocity in Cartesian coordinates is this, but the derivative of constants is simply 0. So the velocity is just y dot u sub y. And the acceleration, second derivative in coordinates, but since x and z are constants, we will have double dot of y uy. Now imagine we have an helix of radius a, and we have a particle that moves up along that helix. An helix in cylindrical coordinates is just simply the radius is constant, let's call it a, and the height varies with the angle as, let's say, a constant multiplied by phi. So the position vector in cylindrical coordinates would be just simply substituting a ur plus z uz, but z is b multiplied by phi. The velocity we derive in time. We take the expression of that sheet of paper I commented before. R dot in this case is 0 because R is constant. And if we just substitute z dot by b phi dot, then we've got this a u phi plus b uz multiplied by phi dot. And the acceleration, we take it from that sheet of paper, and we just simply adjust according to the situation we have. R dot double dot is 0 because R is constant, and we simply substitute z double dot by the constant b phi double dot. This situation has only 1 degree of freedom because z and phi are linked by this constriction here, that z is b multiplied by phi, the equation of the helix with constant radius. So the acceleration would be just this expression here. And finally, imagine a cone with the angle that one of the sides of the cone forms with the z-axis. Let's call it theta 0. And imagine a particle that can move on the surface of that cone. So this means that theta, the spherical theta angle, is constant, and we have 2 degrees of freedom that are the radius and the azimuthal angle. So the position vector in spherical coordinates is r ur. The velocity in spherical coordinates is this, but theta is constant. And if we just substitute theta by theta 0, we got this here. And for the acceleration, we take the expression, and then we substitute theta dot equal to 0, and sine of theta, we substitute by sine theta 0, and cosine of theta cosine theta 0. So we would finally get this here. And this is the expression of the acceleration of this situation here of a particle moving on the surface of a cone. So I hope with these examples you get more familiarized with how to use this expression of position, velocity, and acceleration depending on situation. So all we have to do is get this sheet of paper here from before, and depending on the problem that we have, apply these expressions and substitute accordingly r dot or phi dot or whatever the situation is, as we've seen here with these examples. So thanks very much. Here I give some suggested reading. The usual books, Spiegel, where lots of solved problems, you can find there lots of solved problems. Kibble from Imperial College, very good book in classical mechanics, Landau, Lifshitz, and Mario. Thanks very much, guys, for watching, and hope to see you in next video, and practice math and stay curious. Bye bye.